and compared it with the old handbook, it was the same. Because of this. And it became a real brouhaha within the company. Pug Piper was no longer with the company. And the sales department said, you know, hey, we've been advertising this kind of a speed, and we know you got 10 knots of airspeed increase with the new wheel pants, but we can't show it. Still today, if you go to work at Piper, you'll find this still exists. We were never able to totally relate it. In fact, I had the whole company tied up for a while because I was not going to, what they wanted me to do was just add 10 knots onto the existing fly. I said, I said, you know, I said, in this case, I had a FAA responsibility, which was to make sure the handbook was accurate. The sales guys were going bananas. So what finally happened was my compadre in Vero Beach signed off for the original data. I signed off for the 10 knot increase. But don't believe what the handbook says. Okay. Anyway, that's a little, another war story. A true war story. Well, wingtip booms, nose booms. Again, pitot tube, generally the static ports are located about 10 diameters back from the probe so that the flow is static. Sometimes we mount these things on a swivel, and that allows the pitot probe to always stay aligned with the relative wind. And that's good at very low speed because you may get angles of inflow angles well in excess of 20 degrees. So use that. But the problem with those things is that they have a flutter frequency, okay? So they may flutter at very high speed. So generally we use the fixed probe at high speed if we use a wingtip or nose boom and a swivel probe at low speed and a fixed probe at high speed. However, when you get to very low speeds on this kind of thing and you get high inflow angles, you're going to start seeing total pressure in the static ports. And so for high speeds, the fixed probe is not really good. Well, a wingtip boom should be located at least one local card length ahead of the wing. Now, notice that it says local card length. Most wings are thicker at the root than they are at the tip, right? They're tapered. So, locating at the tip, it doesn't have to be as big a boom. On the Cherokee 6 that we're going to fly in this course, the wing is rectangular, and so you have to have a pretty good sized boom. We're going to make one this fall, that we can put on the Cherokee 6. And I've already got the piece of tube that's 8 feet long. And those booms should be at least 1.5 fuselage diameters ahead of the nose. Nose boom on a 747 or an Airbus A380 would have to be really long to be 1.5 fuselage diameters. Those are big airplanes. In fact, we were up at Gulfstream this summer, and we were commenting that they had nose booms on their G500s or G650s, And they weren't quite long enough to meet the 1.5 fuselage diameters on the thing, because a GE 650 is a pretty big airplane in diameter. You know, I mean, it'll haul 20 passengers or so. Well, trailing bombs and cones. Boeing usually uses the trailing cone, and they attach it to the top of the vertical fin. And if you use it behind the fuselage, it should be about 1.5 fuselage lengths behind the fuselage. Now, Boeing uses it up at the vertical fin, so it isn't affected as much by the fuselage weight. And so they'll mount it up on the vertical fin and just let it hang down, you know. Occasionally it drags the ground when they slow down, but they use it that way. But what it does is you have a funnel with holes in it, and I have one again. I'll make sure we bring some of these things in the back of my airplane right now, but we'll bring some of these things over for you to have a look at. But it stretches out behind the airplane, and then, you know, the tubing that's connected to it has holes in it for getting dispensing static pressure. And the real purpose of that drag of that cone is just to stretch the tubing out. Here's some examples of them. On the bottom picture, look right there. This is an Airbus A320, but they're using a trailing cone. You can see the cone here. Static source is probably up here someplace, you know, ahead of this. They connected to this. And this is the trailing bomb. Actually, it probably should be down a little further. That's going a little too fast, putting it up that high. That's one of the problems with that device, is because of the drag. As you go fast, it tends to fly up behind you. Trailing cone, as you go too slow, its own weight begins to cause it to sag. For instance, a fellow by the name of John Cochran, who worked for NASA Ames, when they were doing an airplane called the Quiet Short Haul Research Airplane, which was a de Havilland, wasn't the Twin Otter, but it was one de Havilland airplane. I can't remember what model it was now, but had 2 jet engines mounted on top of the wing, and it blew the upper surface of the wing. And it could fly real slow. In fact, it could get lift coefficients up around 6. And it would fly, it flew approaches at 65 knots. And they tried a trailing cone. Trailing cone would just, you know, when they'd get real slow, trailing cone would, you know, sag and just kind of wasn't very good. So again, trailing cone, you have to be going at a certain speed in order for it to work. On the other hand, the trailing bomb, which is real good at low speeds, isn't very good at high speed. So you can see, for instance, when I worked at the beach years ago, we would use a trailing bomb to measure stall speeds, and we generally use a wingtip boom for everything else, because of these problems we just talked about. Well, I've already mentioned this. The trailing cone should be at least 1.5 holes in the tubing, actually, not the trailing cone itself. But the static pressure hole should be 1.5 fuselage length behind the airplane. Low airspeeds near stall, its weight causes it to sag, and you get total pressure in the static hole. Trailing bomb. Again, interesting thing about this is, you would think maybe you just trail this thing down here and you had had a transducer that read the static source and sent it back up to the airplane electronically. Problem with that, because you're trying to measure the static source or static pressure where the airplane is, and this thing is down here, it's measuring it down here, and if you send it up electronically, you've got this unknown height. So how do you fix that? You connect it with an actual tubing. And so then the air in the tubing gives you the correct reading at the airplane. Good at low speeds, but drag causes it to fly up and introduces a error. All these devices have their strong and weak points, so you may end up using more than one in a flight test program. And you connect them to a separate set of pitot-static instruments. Once you get those things calibrated, then you can calibrate the ship's instruments. And that's how we do that. That's, well, we have a completely separate set of instruments for you all in the Cherokee 6. Those are the ones you're going to be using. Pilot, me or Tommy, whoever is the pilot in a given flight, has our own set of instruments that are hooked to that underwing thing. They will not read the same. Do not expect them to read the same, okay? So whoever's in the right seat, if you record those instruments, it won't be the same as what the folks in the back are getting, okay? So just keep that in mind so you don't get, so it doesn't confuse you when we do this. Okay. Production installations, we can't use a pitot-static boom as a rule or other devices. So we locate the static source on the airplane, and generally either aft fuselage or underwing are the places where that occurs. Well, we've already mentioned this, at least that first bullet, well, the first two actually. The FAA requirement is that these instruments have to be accurate within 5 knots or 3%, whichever is greater. And that is the position error, not the instrument error, okay? The instrument may have additional error. And what you see in an airplane handbook does not, the error that's given does not include instrument error. Okay? Because this error won't change if the instrument gets broke. You just put another instrument in and you have the same error, same position error. You don't have the same instrument error, but you have the same position error because it's a function of the airplane and not the instrument itself. A lot of pilots don't understand that. Well, how do we calibrate these things? Actually, you need to have both of them calibrated. So we give you in your handout, in your lab book, the instrument error for the instruments you're going to be using. We do not have them. We do not have the instrument errors for the instruments that I use to fly in. Okay. You can calibrate it on a calibration bench with a water manometer for airspeed and a mercury manometer for the altimeter. Well, to determine that position error, we have a number of different methods. We'll talk about those. First one that I started using back in the 60s, 1960s. I've been doing this stuff this long. It's half a lifetime or more for most folks. But anyway, was out in Kansas, and Kansas is a great place for speed courses, because Kansas was settled after we had figured out that we needed to survey land. And so Kansas is all laid out in nice squares. You know, they section lines, we call them. A section of land is 640 acres. You know, it was divided into four, that one section was divided into 4 quarter sections of land, and 160 acres was used for the Homestead Act. Okay, so Kansas is all laid out that way, and it's all north, south, east, west. So you had a couple of miles. It turns out that's, a couple of miles you can lay out on there, and the FAA wanted you to have a speed course that was at least 2 miles. And so what you did is you flew low enough that you could see something on the ground and line up, say, the leading edge of the wing with a point on the ground. I'll say this is the end of the course. We come flying it over low, and as a flight test engineer, you had your stopwatch, and as you crossed this end, you hacked your stopwatch and you flew at the same airspeed, or attempted to fly the same airspeed. And this was all part of it, because to fly the same airspeed, you need real smooth air. Well, in Kansas, the wind blows a lot. And when the wind is blowing much, the surface roughness causes turbulence down low. And when the sun comes up, it heats up the different fields that are there. You know, one's green, one's brown, and so you get these thermals, and makes it really hard to do that. But anyway, you hack your watch, you fly all the way down to the other end of the course at the same airspeed. And as you cross this end of the course, you hack your stopwatch again, you write that number down, and then you zero your watch. And the mistake we used to make, or still made if you fly a speed course, is failing to zero the watch. Go out here and you turn around and you come back and you fly the opposite way. Same thing, at the same airspeed. Hack the watch again, pass the other end, you hack the watch again. Now you've got 2 times that are different due to any wind that's there, right? So if you average those 2 out, you have a speed that you actually flew, all right? 1 airspeed that you flew. So if you're going to calibrate it, say from just above stall speed, let's say 70 knots to 100 or 200 knots, every 10 knots, you're doing a lot of this kind of flying, okay? And if you have to have good weather conditions to do this, it takes a long time. And with a brand new airplane with maybe an untried engine, you're doing this just more than 1 wingspan above the ground. What if the engine quits? You better hope there's a nice field there you can land in, right? Like I say, the FAA said this distance had to be at least 2 miles. The faster you go, if you know at real high speed, maybe you want it 5 miles. So you had to have a measured course, And usually we had a north-south course, and in Kansas that was fairly easy to do because of those section lines. A north-south course and east-west course, depending on where the wind was blowing, because you wanted it to be a crosswind if there was wind, so that it didn't factor in too much. You don't want it down this way because it messes up your data. Okay? Flown twice in opposite directions at the same airspeed. Cancel out the effects of wind. Wind over the course is a crosswind, so it's necessary to have a north-south and an east-west course. So it's a crosswind. Time to fly the course is measured with a stopwatch, and ground speed is determined in each direction. And average to get a no-wind ground speed. And then that's corrected to the instrument corrected indicated airspeed to determine position error. Okay, so that's one method, and that was the primary method we used in general aviation prior to 1990.
What time of day did you fly?
Early. That was the other thing. Oh, dark 30, okay? You were up 3 o'clock in the morning, get to the airport before the sun came up so you could get out on that speed course just as the sun was coming up, you know, enough light that you could actually see the ends of the course. Why? Because less turbulent, smoother air. So this flight test thing is an early morning business as a rule because of you're looking for smooth air most of the time. And for this, that was really the case. And so it was, you know, I lived on the far side of Wichita from Beach Aircraft. So I would, like I say, get up about 3 o'clock in the morning to get over there to try to fly a speed course. Now the military has favored this method, so-called tower flyby. The speed course calibrates both the pitot and the static all together, okay? The tower flyby only assumes that the pitot has no error whatsoever. Okay? However, with the tower flyby, what you do is you fly in this tower. We have a transit, and it's at a known height, and usually we have an airspeed indicator in there, a calibrated airspeed indicator in the tower. The airplane comes flying by the tower. We measure over a known point, usually a runway or something like that, out from a tower. So we have a known distance. This is a known distance. We find this distance, okay, through the trigonometry. And one thing I've found in engineering is that you will find that you use algebra and you use trig. You won't use much of the rest of the math you do. You need to know that a derivative gives you the slope of a line and that an integral covers the area underneath that curve, and that's about what I remember about higher math. And by the way, I had it twice. Okay, but that's about what I remember about higher math. But anyway, you will use algebra and trig, and you know. So, and here's a case where you use trig to determine this height. You know this height. And you make a comparison, you know, you add this, so that's the airplane, and he flies by, and the tower says read, and everybody reads their instrument at the same time. And that way that you know what he is reading, then you can determine, you know, what the error of his instrument is. And then for airspeed, there's an equation that allows you to convert that error into position correction. Calibrated altimeter is located in the tower. And it's reading plus the measured height of the airplane above the towers compared with the reading of the airplanes out there. And as I said earlier, there assumes no error caused by the pitot probe, but all the error is caused by the location of the static source. Third method's called the pace, another airplane, but it has to be calibrated. Most companies at the time tried to keep a pace airplane available in the speed range of whatever was being tested, so you could do a pace method when you couldn't get a speed course or a tower flyby. Again, the tower flyby has the same problem to a degree that the speed course method does, because you gotta fly low enough for them to see you in the tower. And if it's bumpy, holding steady is a problem. So in this case, two airplanes, maybe this is our test airplane, or this is our pace airplane here, and this is the airplane that we're actually calibrating. We go out and we fly formation, and the test airplane, or the pace airplane will stabilize on a speed. The other airplane, stops the relative motion and says read, and everybody reads their instrument at the same time.